All right. Final section. Forces dependent on velocity. This is um, the hardest section in the whole notes, and it's probably one of the hardest sections in all of AP Physics C because it's a lot that you have to wrap your head around here. Okay. We start with a block of mass m that has initial speed v naught. Okay, this is important, and the only reason I'm saying this is because this means that at t equals 0, v is equal to v naught, okay? And that's important for us to know for something that's going to happen later on down the line. In addition to weight and normal force is subject only to a resisting force. This is F, it looks like F sub v equals negative kV. So this is like a, maybe something like a drag force, okay? Or maybe like a friction force or something that resists it, and it's varying it varies with the velocity, right? It always opposes the block's velocity, so it doesn't matter if it moves to the right or to the left, then it'll go. Then it'll oppose the velocity, okay? So really quickly, it's going to ask us to write a differential equation that relates to the velocity of the ball and the time. Okay, well, wait, what's a differential equation? This is an equation that has a derivative in it. Okay, it's an equation that has a derivative in it, and that's all it is. Okay, I'll give an example. Okay, I'm going to kind of section off this part because I really don't need a lot of space to actually solve this part of the problem. But we've been looking at algebraic equations. Okay, and then we now are going to look at differential. Okay. So an algebraic equation might be something like 3x minus 9 equals 12, okay? And then you add the 9 on both sides to get 3x equals 21, and then you would get x equals 7, right? Okay. Um, that's an algebraic equation. That's just kind of an example that I'm coming up with off the top of my head, okay? A differential equation might look very similar to this, but it has to have a derivative in it, and that's going to be 3, that would be something like 3 dy over dx, okay, minus 9x equals 12. And then if you solve for dy over dx, okay, that's what we're trying to get this in terms of. You would subtract the 9x from both sides. You would get 3 dy over dx, okay, equals 12 minus 9x, and then divide both sides by 3 to see that you would end up getting dy over dx equals 4 minus 3x. And you notice that differential equations give you an expression, not a value, right? Algebraic equations give you a value. Differential equations give you an expression, okay? So in physics, particularly in physics C, in mechanics, when we're asked differential equation, okay, when we're asked, particularly in mechanics with mech, if we are asked to find a differential equation, that is a dead giveaway as to what you're going to do. If it's asking differential equation, mechanics is always some form of Newton's second law. Okay, that can be either F equals ma, or it can be torque is equal to I alpha, right? Those are some examples of Newton's second law that we've seen in physics before. So let me draw the forces really quickly on here. We've got normal force going up, okay? We've got mg going down, and then we have that kv to the left, okay? Negative kv to the left, okay? So to write our differential equation, we need to start with Newton's second law, which is going to be F net equals ma. That's a good starting point. That's Newton's second law, okay? And you'll notice that the only force in the horizontal direction, normal and mg cancel each other out, but in the horizontal direction, you just have negative kv. So you would set the net force would be negative kv equals m times a. And now you're thinking, okay, well, this isn't a differential equation because we don't have a derivative in it. Except we actually technically do have a derivative, okay? And we actually do have a derivative because acceleration is the derivative of velocity. Would that make sense? Can I write this like this? Can I do negative kv equals m dv over dt? Heck yeah, I can, and I just did it. Okay, that's perfectly fine. So this is the differential equation right here that relates velocity with time, okay? So now I need to show you the process of solving the differential equation to obtain the velocity v. Now in calculus A, B, and BC, you're only ever going to look at first order differential equations that are already separated. Okay. In this class, you actually have to use a strategy called the separation of variables, and that's going to be our first step right here to solving it. We have to use something called separation of variables. Okay. To actually solve the differential equation. And it's literally exactly how it sounds. Separation of variables means that we need to get, okay, get v and dv on one side, and then get t and dt on other side. Okay. Now, notice that we don't have any t in this equation. That's perfectly fine. So then we don't really care what ends up on that side with the dt. Okay. There's things that we can do to make it easier, but we don't necessarily need to worry too much about that. Okay. Okay. Now what I'm going to do, okay, is I'm going to write out. Just going to take my expression up here. Negative kv equals m dv over dt. Okay, and I need to figure out, okay, well, what can I do? Okay, what can I do to get the v's on the v and dv on one side and then dt and t on the other side? Well, we don't have any t's, okay, so we don't really need to worry too much about that. But we need to get the v's on the same side. The easiest way, in my opinion, to do this is I'm going to divide v on the left-hand side. Okay, I'm going to divide v on the left-hand side. And then I'm going to multiply dt on the right-hand side, so that's going to multiply to both sides, okay? And then what I'm going to do is I'm actually going to, you don't have to do this, but I think it's easier to do it. You want to move the m to the other side, so I'm going to divide by the m over here too, okay? So I'm dividing on both, I'm doing these operations on both sides, but I'm only illustrating them on one side, okay? So then what you're going to end up with is you're going to get this expression negative k over m on the left-hand side, dt equals, okay, equals dv on the top over v, okay? And this is the same thing as just 1 over v times dv, okay? That's fine too. You can say that. That's perfectly fine, okay? Okay, well now what I need to do, I'm all set to integrate. What I'm going to have to do is I'm going to have to now integrate my function. Okay, the second step here would be to integrate both sides with respect to whatever variable is paired with the d, right? So I would integrate the left side with respect to t and integrate the right side with respect to v. Now here's something cool to know, okay? Here's something kind of cool to know, is that on the left-hand side, k over m is a constant, okay? So that would actually get factored out of the integral no matter what. So I actually don't even have to take the integral of the whole thing. I can just take the integral of the dt and call it a day. Okay? On the other side of the equation, right, I can do the whole thing. I can just take the integral of the whole thing. Okay? Now, when you take the integral of both sides, the left side is really easy to take the integral of. The integral of dt is just t. Okay? So we would be left with negative k over m t plus c, okay, don't forget that plus c there, and set that equal to, okay, this is 1 over v, right? So the integral of 1 over v with respect to v is just going to be natural log of v plus c. Now I'm going to do something here that will probably make your math teacher flip, because what's going to happen is these are two separate integrals. Those c's are not the same. These two c's are not the same, okay? This constant on the left-hand side is not the same as the constant on the right-hand side. So here's the issue now, okay? We have two unknown constants, but in physics, you're going to learn something that we don't care, right? You're going to learn something about physicists is that we kind of don't really care too much about what those constants are, because, watch this, if I take on the right-hand side, if I subtract the c from the right-hand side and then move it to the left-hand side, okay? If I subtract c from the right-hand side and move it to the left-hand side, okay, Well, those two c's aren't the same, so it's not going to be 0. Maybe they are the same and it is 0, but we can't just automatically assume they're the same. But wait a minute, I'm taking a constant and I'm subtracting a constant from that. Wouldn't that just give me another constant? Oh, yeah, it does. It would just give us another constant. Okay, wait. If it gives us another constant, can I just call that C? Yeah, that's fine. We can do that. Let's do that. So that's what I'm gonna do. Okay, I'm going to now do. So what I'm going to do is I'm going to continue it up here. Okay, what I'm now going to do is I've got negative k over m t plus c. This c right here is actually a new constant that I made by subtracting the constant on the right-hand side, okay, and moving it to the left-hand side. This is not the same c as we just got right here, even though it is. Now, in calculus, you probably will have like C1, C2. That's not my issue, though. I don't care about that, okay? I'm a physicist, okay? We get straight to the point here, okay? And then we set that equal to natural log of v, okay? Now, here's the thing that's important to consider, okay? I am not looking for a natural log of v. I'm looking for v. So how do I cancel out v? Easy. I raise whatever's here to make it a power of e, right? Okay. So I'm putting an e. I'm raising both of these, right? I'm putting them above e. Wait a minute. I've taken algebra 2. I know that if I have this expression right here, this is the exact same thing, right? E to the negative k over m times t plus c is the exact same thing as saying e to the negative k over m times t times e to the c, right? You see how those are two separate things? Okay. Okay. Wait a minute. And watch, this is where like your math teacher's probably already begun to crash out at this point, okay? Wait a minute, Mr. Mitchell. Isn't e to the c also a constant? Isn't it? Isn't it a constant, right? E to the c? If c is a constant and you were just taking e and raising it to that power, isn't it not just another constant? Okay. So guess what? I'm just going to call this c, right? I'm not even kidding with you. I'm literally just going to call this c. So this is really just c times e to the negative k over m t times t equals v. That's it, right? That's all you got to do. Now, I've solved for v, but here's the issue. Now, I suddenly care about my constant c. I don't want it. I don't want that constant c anymore. I don't want it, okay? So I need to use what we call initial conditions, which, believe it or not, are the conditions you initially have to solve for this c, okay? So how do I use my initial conditions to solve for c? Well, let's find out, okay? What are my initial conditions? Well, my initial condition says at t equals 0, v has to be v naught. So I'm going to take my expression that I just got here, and I'm going to replace it with the initial conditions. V is equal to v naught. So instead of writing v here, I'm going to write v naught is equal to, okay, c times e to the negative k over m. And at what time is it v naught? Oh, it's 0. Okay, so this up here is actually multiplied by 0. Oh my gosh, wait a minute. So that turns this entire exponent into 0, right? This whole thing becomes 0, okay? So then e to the 0 is just what? Oh, it's e to the 0 is just 1, right? So then v naught equals c. Oh, wasn't that like quick and painless, right? So now what I've got, okay, is that I've got v naught is equal to c, okay, and now I just take this and plug it back in to the equation right here. So we can actually get the proper equation v equals v naught times e to the negative k over m times t, okay? And that right here, this right here is your differential equation. You've actually just solved it, okay? You've just solved your differential equation. There it is. You're expressing v as as a function of t with no constant in it. Congratulations, you've done it. You did k and m. We use those. That's fine. T is there too. That's great. Okay. And then v naught, that is just that's a constant, right? So I guess we don't really need to worry too much about that. Okay. Okay. Now, this is just your base velocity function. You're not out of the woods yet because there are other things that you're going to have to do with it. Okay? You're going to have to be able to integrate and take a derivative of it. Okay? I just realized I didn't really number my steps here, but that's okay. I think you can kind of follow along with what I did. Okay? Now, I can take the integral or the derivative of it. Now, actually, let me show you what this function looks like. So what I'm actually going to do is I'm actually going to go into Google. Okay? That's not it. That's my YouTube channel. Sorry. Okay. If you go to Desmos graphing, okay, I'm going to go into Desmos, and what you should see, okay, is if I input this equation that we've just got, it's going to be, I have to use it in terms of y and x, okay, y equals c, that's just my constant, okay, or maybe v, okay, times e to the negative k over m times x, because it needs to be in terms of x in order for Desmos to actually understand it. And I put all the sliders here. I'm going to change my window here to be 0 to 10, okay, and then change it to be 0 to 10, 10, okay. So then you should see that the function looks like really funky, okay. Can you see that? Okay, let me move my face up here into the corner so that you can actually kind of see it. Okay, do you see right here that the velocity, right? If I change the velocity, you can see that as it goes up, right? I'm actually changing the intercept right here. So if I make this a value, like a really nice value, let's say maybe something like 2. Oh, what the heck did I just do right there? I'm not very good with the keyboard, clearly. If I make this a value like 2, okay, then you're going to see that my intercept is 2, right? Do you see that right there? My intercept is 2, okay? If I make this, like 3, you're going to see my intercept is also 3. So that constant is really determining my intercept of the function, okay? Do you see that k? So k, what k represents is something called the drag coefficient, okay? It's kind of like the coefficient of friction where it's got to be between where it's basically just kind of some indicator as to basically an indicator as to how much air resistance that exists between things or drag force exists there, right? This is drag coefficient. If you notice that I increase my drag coefficient, let me actually increase my v. Okay, let me increase the v up to 10 so you can actually see like the trend really well. You notice that if I increase the drag coefficient, it actually makes the graph steeper, which means that my velocity is decreasing faster. Okay, so the drag force is essentially becoming stronger. Okay, and then if I move this back to, let's say we make the coefficient just 1, okay, then if I take the mass, if I increase my mass, well, mass actually quantifies your inertia, right? The more mass you have, the harder it is to get you to change your motion, right? So the more mass you have, the less that the drag force um, affects you, right? You can see that the more mass you have, the more that you can see that the more or sorry, the less steep of slope this kind of has, right? So if you have a really small mass, you have a really, really, really steep slope, but then if you have more mass, it starts to kind of flatten out because it's a lot harder for it to change your motion, okay? Okay, so there's that. Let me go back to here so I can show you what's going on here. And I don't know why my camera's suddenly become very blurry. Okay, I have to put like my hand up against it and then bring it back towards me so that you can actually like see kind of my face, okay? Okay, so as we saw earlier, the velocity function is just starts at v naught, right? That's our intercept, and it's going to look kind of like this. This is what we sometimes call the exponential turning off function. Okay, this is like a turning off function because what you can think of it as is it starts at some value and it turns off towards something. It's going to asymptotically approach zero. Okay, your velocity is asymptotically approaching zero here. Okay, or it'll asymptotically approach some value. Okay. For the other graphs, it's going to look very similar, but for example, I'm sorry, I'm trying to get my camera to work. It's bothering me how my face is blurry. Okay, there we go. That's better. It'll asymptotically approach zero. Okay. Now to get the acceleration, you need to take the derivative of this function that we just got right here. Okay. And that's actually really easy because all you have to do is use the chain rule, right? So to take the derivative of that, I'm just going to rewrite at v equals v naught times e to the negative k over m t. This is actually, you'd have to chain rule this because you have an interior function, which is negative k over mt, and then you have the exterior function, which is this whole mess right here, okay? So when I take the derivative, what I'm going to do is I'm going to do a equals v naught is a constant. It's going to get left alone. Okay. Then what I need to do is I need to this is my function right here. Okay. I'll just write it just like normal because the derivative of e to the something is just e to the something. It's itself. Okay. E to the negative k over m times t. Okay. Then I need to take the derivative of the interior function here. Okay. Which would just be negative k over m. Okay, so that's my derivative right here. And the way that that's going to look in like a really nice condensed form is just going to be uh, uh, negative k v naught over m, okay, times e to the negative k over m times t. Okay, so that's how that's going to look right there. Okay. So there's your acceleration function right there. And this is also a turning on function, or sorry, a turning off function, okay? That's also a turning off function. So it's going to start at a maximum value of k v naught over m, and you should notice that the maximum value, or sorry, the starting point is going to be this function right, or sorry, this part right here that comes before the e. Okay, that part right there is going to be your maximum, or sorry, where you start, right? So or your maximum, sometimes it'll be like your asymptote, okay? But this value right here, and you notice I'm just doing positive, right? Doesn't really matter. I know there's a negative right here. I'm just doing for the magnitude, okay? This is going to be another turning off function, so it's going to look kind of like this, okay? Maybe a little bit steeper than that at the beginning, okay? Now to get the position, you have to integrate, and this is actually where like the biggest struggles come from. Position is really weird. Okay, position can be really weird. To integrate this one, right? So here's what I'm going to do. I'm going to have to integrate the velocity function right here. Okay. So where is which pen do I want to use? I'm going to use red pen for this. Okay. So what I'm going to have to do is I'm going to have to integrate this function right here. Okay. And when I integrate it, it's going to look like it's going to be kind of a mess because what's going to happen is you're going to have this is v equals v naught times e to the negative k over m t. When you integrate it, you actually have to use u substitution. Okay, so if I'm going to integrate it, right, integrate both sides. Okay, if I'm going to integrate it, then what's going to happen is actually I don't even need to integrate over here because I would just make this x. Okay, that's my position. Okay, if I just integrate this, okay, I have to use u substitution, right? Well, let's make u equal to negative k over m t, and let's make du. Du is the derivative of this function right here. That's just going to be negative k over m dt. Okay, now here's the thing. You'll notice, okay, that when I'm integrating here, right, I should also add the dt on the end here, okay? When I'm integrating this, you'll notice that I don't have a negative k over m to spare to pair with the dt to give it the to make it into du, right? In order for me to make dt into du, I need to have a negative k over m on with this, right? Well, here's the thing. Wouldn't you agree that I can just multiply, if I multiply both sides by k over m and m over k, right? Well, k over m is the reciprocal of m over k, so it gives us, it's basically the same thing as multiplying by 1, right? So if what I do here, okay, if I multiply by 1 on both sides, but instead this 1 on the right-hand side, I'm going to make it k over m times m over k, because those cancel out to 1, then I can actually turn the right-hand side into du. Let me show you how that works, okay? I'm multiplying the left-hand side by 1, so that's just x. That's going to be fine. It's not going to do anything. Okay, let me actually switch to a different color here to blue so that I can actually, okay, that's going to be x, okay. On this side right here, v naught is a constant, but you know what else is going to be a constant? It's going to be that m over k that I had just brought in, okay. So it's going to be m over k times v naught, and then the integral is e to the u, okay, du. Okay? So now what I've done, right, is I can now turn the dt into du because I will have a term in here, right, that is k over m. If I multiply by k over m and I multiply by m over k, you understand that that resolves out to 0, right? And then I just multiply by 1 on the other side, right? I mean, 1 is the same thing as m over k times k over m, right? That's the kind of hard part to wrap your head around, okay? So then, when I integrate it, I'm going to get x equals m over k v naught, okay, mv naught over k, times e to the u, though the integral of e to the u is just going to be e to the u. Nothing's going to change with that, okay? So this is going to be e, okay, to the negative k over m times t. Okay, there's my integral. Okay. Okay, there's my integral right there. Okay, so, oh, and so I'm so sorry. There needs to be a plus c right here. Oh, I'm so stupid. Now, here's the thing. Now you need to figure out what that plus c is. Oh my gosh, what a mess, right? Oh, I hate figuring out what plus c is. I hate it. I hate it. Why am I taking this class, okay? So, to figure out what the plus c is, okay, what you have to do is plug in your initial conditions. Initial conditions say that our initial position should be 0, okay? mv naught over k, that's just going to be a constant. Okay, so we'll leave that there. E to the, okay, well again, time's going to be 0, so the whole thing right here is going to end up being 1. Okay, plus c. And hopefully you recognize, okay, that c, this c that goes right here, is going to be negative mv naught over k. Okay? So this c right here is the same as this c right here. Then you just plug that in. You get x equals, you then end up getting x equals mv naught over k times, I don't know why I'm drawing a parentheses here. It's because of the next step. E to the negative k over m t plus, or actually, sorry, it would be minus mv naught over k. And then what you actually can notice, right, is that you can actually factor out the mv naught over k, and you would end up getting a funky kind of equation. If I factor out a positive mv naught over k, then it's actually going to make this look kind of weird, okay? You would actually have to swap these terms inside right here, and so it would be x equals mv naught over k, parentheses 1 minus e to the negative k m times t. Okay? This function right here is what we call the turning on function. And the reason we call it the turning on function is because, okay, turning on, because what it is you're going to notice that it looks kind of similar to these, but other way around. We start at 0, right? And then we asymptotically approach some value. In this case, the value is mv naught over k. Okay, so here's our value. I'm going to draw a dotted line to show you that we asymptotically approach it. Okay, and we asymptotically approach it. Okay, see how that works out? Okay. What a mess. That's just, it's terrible. It's terrible how this whole thing works out. Okay. But, it is what it is. And, it is what it is. Okay. Um, so there's that. Okay. Well, gosh. Okay. Um, all right. I think actually now that I think about it, I might have actually missed a negative somewhere. So this part right here that I circled is correct right here. Okay, this should actually be negative. I'm so sorry. This should actually be negative, which kind of leads the whole thing here to be negative. Okay, and then you would, when you factor it out, you're factoring out a positive, which actually is what causes the terms to kind of swap here. Okay, so this would actually be plus, and then it would swap here. So it should be positive right here. That's my bad, okay? But that's okay. It's the same thing. I gave you the same thing anyways. I just flipped the signs, okay? Okay, here's a different example. This is a one now with air resistance, okay? This is air resistance acting on something. Okay, the first thing I want to talk about really quickly with this air resistance problem is, okay, first off, now you see why we don't ever use air resistance in physics 1, right? But air resistance as it falls, it's dropped from rest. That's our initial condition right there. So this says that V is equal to 0 when T is equal to 0. Okay. And this right here is KV, and this right here is mg. Okay. Right? You have KV going up and mg going down because this is always a resistive force that opposes your motion. Okay. I drew the forces on the ball. Good. We got that. We're good. An expression for the terminal velocity. Okay. Terminal velocity means that when an object has fallen for enough time, it eventually it speeds up as it falls, but eventually it hits a point where it's just going to go the same speed until it lands or something happens, right? But if it kept falling, it would just stay at the same speed. So eventually, you notice the speed it increases, and then eventually it hits a point where where it's going a constant speed the entire time. Okay. So to write the expression for terminal velocity, I would have to start with Newton's second law, right? F net equals ma, and then the force going with, so right, I'm going down, so that would be mg minus kv, my resistive force, equals ma, right? Well, I'm going to take this expression and I'm going to use it to get my terminal velocity. Except here's the thing. If the terminal velocity is the fastest that the object's ever going to go, it's not speeding up, it's not slowing down, which means acceleration is 0, right? So then you get mg minus k. I'm going to write this as vt for terminal velocity equals 0. Oh, okay. Let's add kvt to both sides. You get mg equals kvt, and then you get vt by itself to get vt equals mg over k. All right, there you go. That's your expression for terminal velocity. Now, guess what? We're actually not going to circle around back to that here for just a second, okay? We just derived it real quickly. We're going to circle back around to it here in a second. I don't have any water in my hydro flask. This is a crisis, okay? Now, here's the part where we have to write the differential equation. When we do this, we're actually going to just, when we do this part, we're actually just going to take this expression up here that we wrote and use that to write our differential equation. Okay, we're not going to do anything with terminal velocity. We're just going to use the part up here. Okay, so when I write the differential equation, we should get mg minus kv equals m times dv over dt. Okay. Okay, so there's that, right? So now I'm going to show you how to solve the differential equation. We just got to do the same thing we did last time. The first thing we need to do is do separation of variables. Okay, the first thing that we're going to do is separation of variables. So let me show you how to do that. Okay, we've got mg minus kv equals m dv over dt. Now, believe it or not, the easiest way to do this, okay, the easiest way to do this is to just divide the mg minus kv, all of it from the left-hand side, and leave yourself with a 1 on this side, which is like, you're thinking, why would we do that? But it actually is the easiest way to do it, okay? So I'm going to divide mg minus kv from the left-hand side, and also from the right-hand side, okay? Then what I'm going to do is I'm going to multiply the dt here to get that to the other side. And just to make things easier for myself, I'm also going to divide the m here and from both sides, okay? So when I do all those operations, I'm going to end up on the left-hand side with just 1 over m, okay, dt equals, up here, dv on the top, and on the bottom, I've got mg minus kv, okay? Did I forget anything here? Let's see. 1 over m on that side, move that to the other side, move that to... Okay, boom, we're good. Okay, we're good. Now I can integrate. Now here's the thing. I'm going to have to use u substitution for this. I think that's the easiest explanation for this, is to use u substitution. Okay? Now, what you can do, okay, I'm going to do something a little bit different for this one. Okay, when I do u substitution, where's my green? Okay, I'm going to integrate, right, the dt. Okay, integrate the dt, and I'm going to integrate the whole right side, because I can do that, because it's all in terms of v. Sorry. Okay. Now what I'm going to do, okay, and this is not too crazy. Okay, is I'm going to use my u substitution, and for my u substitution, I'm going to make u equal to mg minus kv, and I'm going to make du equal to k dv, or sorry, negative k dv. Now, here's the part where things get weird. Last time what I did was I multiplied both sides by 1, and I was able to make that work out. Now, you can kind of do that for this one. Not really. Okay. You can kind of do it for this one, but not really. Well, you could multiply both sides by 1, doing the trick I did last time. I think it's actually easier straight up to just say, okay, well, in order for I need a negative k in the numerator here. So what I'm just going to do is multiply both sides by negative k, and that's perfectly fine. So if I multiply both sides by negative k, then I end up with negative k dv on the top here, and negative k over m here. So what I'm going to do now is I'm going to rewrite this, okay? It's going to be negative k over m, okay? Integral, okay? dt equals the integral of negative k dv over mg minus kv, okay? Now, do you notice, right? I just multiplied negative k on both sides, and that's fine. That's completely legal, right? The math gods smile upon us because we've followed their rules for once, okay? Now I can do proper u substitution here, okay? And I can take the integral to the left-hand side. That's just going to be negative k over m, okay? T plus c, okay? And set that equal to the integral of du goes on top over u, okay? And then you can see that the integral of this is just going to be negative k over m t plus c equals log natural of u, okay? Plug my u back in, I get negative k over m t plus c equals, and yes, I know there's supposed to be a plus c here, that's fine, but I'm actually going, here, I'll just write it here just for that, okay? but I'm going to take that and move it over to the other side. Okay, so my new plus c is like the new combined plus c that I don't care about. Okay, and that's going to be natural log of mg minus kv. Okay. Okay. Well, that's a mess. Okay, it's a terrible mess. I say that a lot, I realize. But now I don't want natural log of mg minus kv. I want just v, right? So I need to raise everything to the e power. And I'm going to do the same thing that I did last time here, where I do e to the negative k over m times t, e to the c, because that makes my life easy. Okay, e to that, e to that, e to that. Okay. And this right here is just going to become c. Okay. So this is actually going to become this wonderfully beautiful equation. Okay. This is actually going to become a very beautiful equation. C times e to the negative k over m t, okay, equals mg minus kv. Now, here's the thing. Okay. I don't know what c is. Okay. But we can solve it really quickly if you want. Okay. We can figure out what C is really quickly. I'm fine with that. Okay. I'm cool with that. Okay. If you take your initial conditions, V equals 0, T equals 0. Okay. So if we take my initial conditions, here's my little detour to figure out C. Okay. I'm going to make a little box, little math box over here so I can take a little detour and figure out what C is. Okay. If I take my initial conditions, I will get C times e to the 0th power, which is just 1, right? And set that equal to mg minus k times v. Wait, v is equal to 0. Oh, there it is. I made this big box for nothing, right? Because that's it. I'm just plugging in my initial conditions, right? So, e to the 0th power equals 1, right? So that's why that's not there. And then if v equals 0, then mg minus kv just equals mg, right? So that's how I got that, okay? That's just kind of explaining what I did. Showing my work, so to speak. So now I'm going to replace c with just mg. So this is mg, okay, e to the negative k over m t equals mg minus kv. Okay, I want to get v by itself, so I need to subtract mg from both sides and then divide by negative k. And you're going to see that I'm going to end up getting, okay, if I subtract mg from both sides, I will end up getting mg e to the negative k over mt minus, okay, minus mg all over negative k. Now, can I write this in simpler form? Yes, and I'm going to do that, okay, because you can notice that I have an mg in common on both terms, and the negative k is in common on both terms as well. So I'm going to factor out a positive mg over k, and I can do that, okay, mg over k. So I would end up getting mg over k times, and because I factored out a positive even though the k is negative, right? What's happening is I'm actually going to flip these terms here. So this would be, if I factor out the mg right here, this is just going to be 1, okay? And then minus e to the negative k over m times t. And you'll notice, wait a minute, Mr. Mitchell, that's the turning off function right there. Yeah, you're right, it is. It is the turning off function, okay? Turning off, okay? You're like, Mr. Mitchell, that's the turning off function. Yes, it is the turning off function. Congratulations. Great. Gold star. Okay. And so you'll notice that there's a maximum value. The maximum value, or the asymptote, should be at mg over k. So I'm going to do, okay, mg over k. Now, I'm going to start at 0, okay, and I go all the way up to there. Okay. Okay. Then what happens for the acceleration? I have to integrate. Oh gosh, I have to integrate. I hate integrating. I don't actually hate integrating. I love integrating. It's really fun, okay? So I'm going to take the integral of that, or not sorry, derivative. I kept making a big deal about integrating, and I was talking about derivatives. Okay, you actually have to take the derivative to get the acceleration. Okay, so to get the derivative, it's really easy. All you gotta do is, again, the chain rule. Okay, if you do the chain rule, you'll actually end up getting, and I'm going to kind of skip this step here a little bit. You'll actually end up getting, so if you take the derivative, right, this one is going to resolve out to nothing. Okay, so then you would just do mg. So really, it would just be mg over k, or negative mg over k times e to the k over mt. And when you take the derivative of that, you should end up getting a function, and I'm going to write here, it would be mg over k times m over, or sorry, k over m e to the negative k over m t. And basically what I'm doing, right, is this is the chain rule, right? The chain rule at work. So what I've done here is what's in the I did the chain rule, right? E to the whatever, the derivative of e to the whatever is going to be e to the whatever. But then I took the derivative of what's up here, which is just negative k over m. Okay, and you'll notice, oh, wait a minute, Mr. Mitchell, this is actually going to be because this mg over k right here. Actually, I guess I don't really need the negative. Okay, what's going to happen here? You'll notice, oh, k cancels out here, m cancels out here, so you're just left with g, okay, g times e to the negative k over m t, okay? That's all you got to do, okay? Or actually, I guess it would be negative right here. It would be negative right here because technically, right, this e right here would also be negative, and the two negatives would cancel out, so you'd end up with a positive, okay? And so then this right here, oh, this is the turning off function, okay? Oh, sorry, this is the turning on. I should have written turning on. Okay. That's turning on function. This is the turning off function. So it starts at G, okay, and then it rapidly decreases and then kind of asymptotically approaches zero. The acceleration should approach zero because, right, the forces will balance and there's no acceleration in that case, okay? For the position, I'm not going to do the full integral for you because it's a lot, but it is something that you are able to do at the calculus A, B, or BC level, okay? But you should start at zero for position, and then you increase, and you actually have a slant asymptote here, okay? So it goes like this, and your asymptote is actually kind of diagonal here. Why is the asymptote diagonal? Well, it's because what's happening, right, is that initially there's acceleration, right? There's initially acceleration, and then when the object hits terminal velocity, it's constant velocity. So this part becomes linear, right? And the slope here is just equal to the terminal velocity, which we got earlier as being mg over k. Okay? So there's that. Now, let me show you. Now, these are some really complex examples that you can see on the AP test, right? However, I want to show you conceptual ways to kind of shortcut these problems because these problems are long. Okay, these ones are long problems. This is probably the longest video I've recorded for Physics C yet. Okay, but I need to show you the kind of shortcut, the concept behind it. Suppose that a ball is initially thrown down with a speed v naught greater than its terminal velocity vt. Sketch graphs of acceleration and velocity as functions of time where up is positive. Well, if the ball is thrown down with a speed v naught greater than vt, okay, if it's downwards, right, it says up is positive, so if it says down, okay, then I'm going to start at negative, and it's going to be at a speed v naught, which is greater than velocity, so it's going to be right there, okay? We start out there. Now, as the ball is going down, air resistance is opposing it, okay? Air resistance is opposing the gravity. So you've got, right, if you can think of it like this, right, here's the ball. You've got mg going down, and then you have kv going up, okay? And what you should notice, right, is that kv is going, initially is going to be really high because your velocity is really high, but then it's going to kind of try to slow the object down to get to terminal velocity. The object is always going to try and seek terminal velocity, right? That's where it wants to be. So my asymptote is going to be at terminal velocity, and I'm going to basically just do this kind of trend towards it. Okay? Now, for the acceleration, I'm going to show you what it's like first, and then I'm going to tell you why it's like that. You actually start out with an acceleration that's greater than the magnitude of g, and then it flattens, it goes like that. It asymptotically approaches zero. And it should make sense as to why asymptotically approaches zero is because what's happening is that when you hit terminal velocity, there's no acceleration, right? And when you hit terminal velocity, you're done accelerating. So then acceleration is equal to zero. Now, let me show you this because this is something that's really challenging to grasp. Okay, it's really challenging to grasp this, and I want to make sure that you understand it. So I'm going to do sim bucket. This is a demonstration. Okay. And what you can see here is this is like a skydiving one. I'm going to use the gold brick, okay? And what you can notice is that, okay, initially, as it's falling, right, you have that drag force that's going on it. And if you let it fall for a while, then you should notice that eventually what's going to happen is the drag force will end up equaling the weight force. And this is going to take a second for it to happen, okay, as it's falling. Okay, you'll see eventually it's going to get there. Boom, now it's canceled out. It's not going to go anymore. Now, here's the thing to consider, okay? If I throw on the parachute, you're going to notice that immediately the drag force is going to skyrocket and the weight is going to stay constant. It should stay constant. So you're going to notice that as soon as I let go of it and then I throw on the parachute, boom, you have this massive skyrocket of drag force as it falls, okay? And then, so you have this massive drag force, right, as it falls, and then you notice that obviously that acceleration is way greater than gravity in the positive direction, and then you notice that the drag force levels out to then become equal to the weight force. Okay? Do you see how that works? Okay? Now, that's an example of that, but another way to explain it is that if you know that the drag force is directly proportional to velocity and you throw the object down with a strong amount of velocity, then what's happening, okay? What's happening is if you're throwing it down with a high amount of velocity, then what's happening is you're giving it high V, which increases the drag force on it. Okay. The higher your velocity, the greater the drag force. And immediately after you've thrown it, the velocity is the highest it's ever going to be because immediately after you've thrown it, drag force starts slowing it down. Okay. So that's why it's so strong, right? Because mg is going to be constant no matter what. Kv is dependent on velocity. You throw it down with a high velocity, it's going to very quickly try and put it back up to the terminal velocity. Okay? For the other example, you throw the ball upward with speed v naught. Okay? So instead you're throwing it upward. So if we're throwing it upward, we start with a positive v naught. And you know what happens when you throw a ball upward, right? You throw it up and it comes back down, right? So we shouldn't end at positive VT. We should end at negative VT. Okay? And I want you to make a note of this very important location where V is equal to 0. Okay? That right there is when you throw a ball up, when you throw it up, it hits a maximum height, stops momentarily, and then comes back down. That's what this part right here is representing. It's saying that your velocity, it's going up, 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 gets to the maximum point, and then starts to fall back down. Okay? So what we should see, right, if the velocity is equal to 0 here, this is where the acceleration should be equivalent to negative g, because there should be no drag force on it, right? Okay. So that's where it should be equal to g, right about, oh, didn't drop perfectly on there, right about there. So when you throw it up, when you throw it up, right, when the velocity is directed up, I'm not going to draw the velocity attached to it, okay? When the velocity is going up, not only do you have mg going down, but you also have the drag force kv going down. So obviously that's going to give you an acceleration greater than g because you have more force going downwards as it's going up. Okay, so this should be equal to more than negative g, and then it should asymptotically approach the zero from there. Okay, do you see how that works? Okay, because when you hit the top of the trajectory, okay, at the top, okay, at top, the ball does not have any drag force because it has no velocity. It just has the mg going down. Okay? And then as it descends, that's when the drag force is pulling up, and that's when your net force is decreasing, right? Because you now have two opposing forces, and therefore your acceleration is decreasing, and it will eventually decrease down to zero. Okay? Okay. Well, that's that. That's drag force. That's a doozy. Okay. And that is actually all of Unit 4. All right. Well, that is it. All right. Have at it. Have fun. Girl boss it up. Peace out, Girl Scout. Live, laugh, lab. All right. Have fun.